Willkommen to Impossible Prototyping. The tutorial video for today is about the word clock generator. Some ask me to explain in more detail how the algorithms behind this program are working. First, I will go through the program very quick and explain the main details how to use it. And if this is done, I will go through the source code and we will see how the main algorithms work. So when you open the program, you first get 3 tables in the first main tab. And there you can select if you want text change for each minute or, for example, for each half an hour. And here you can also choose between 24-hour mode or AM and PM mode. Here you can change how the text will be arranged. If you want to have hours first or minutes first or AMP first. I think now just for testing I will give me a second. So I filled that in off camera. We can save this now and for example call it English time. So we saved it. And here you can see I can use here the diff hour. When I move this a little bit, you see it's 2:15. So we need the next hour. So we have to add 1 to choose to select the next hour in the table. So that is matching up. And I don't have the o'clock now. And you can also make some modifications here. So when I tell, for example, when it's midnight, it's, I don't know, make it a little bit creepy. And so you can modify special times. So if you want to have some times with another text, it's no problem. Okay, and you see like this is modified together in the way we describe it here. So in the next step, we generate the graph. So when I push on calculate, it's loading every time text and then tries to optimize the graph as much as possible. And then it's mapping the graph into the letter matrix. And when this is done, we can push update here and we get the different matrix sizes which the program finds. So we can go through that and can choose, for example, 9x9, which is a good size. And we see also that there's just 5 cells not used, so this is really good. So this would be a nice example. We can then choose which letter we want to fill it. When we use everything uppercase, then we'll go with uppercase anyway. And then we can see here it's midnight help. Help is displayed, and then we can go through the different times. Okay, and in the last step, I can push export and tell, for example, to export it in test.txt. So now we have the file opened. We see here we have a representation of the text. So you can copy that and use this to generate the mask for the laser cutter or to generate a file which you can print on transparent foil and use that, for example. It depends what you have, and maybe you can also order this from a copy shop and let it like with a foil, also like order foil. So some copy shops can do that. And here we have the generated table. As I told already in the other video before, I have a table for each word, and there it's just telling the metrics where the word is starting and where the word, how long the word is. So for example, help 0, 1, 2, 3, 4, 5. So it's starting at the 5th position, and it's 4-letter long. And the next, like it's counting this way, but I will come later to that. Yeah, In the next step, we have all different texts. So if there's a different time text, there's also written which times represent this text. In this table, there is just written which words are used. So in the most case, for example, here there are used four words, and this is it is the first word, and then quarter to 9 are the other threes. This is done here. There's also a mapping table, so there's a table for a word table, so I can convert the number actually over this table. I can link it to that table. So there I get the link between the number of a word. For example, this is 1, so this is the word 1, and so it is the first word. So this is linked. And then we have the timetable. So there is for every time is actually a reference to the pattern. So if I want to have like when I have two, the hour is 2 and it's half, so I just use this table to look into it and then I get the time string. And for example, we have here for 0 o'clock, we have the word pattern 9, and when we look in the word pattern 9, it's help. And help is the word 0, and when we look at the word 0, it's actually help. So this is how it's working. And in the end, we have the most important table for the user. Here you can tell which LED number is actually on this position. So this table is actually easy to use. You see, aha, this is the letter I. So I have to look, okay, the letter I has the number of the LED, and this number I'm writing here. So I can make any arbitrary mapping between the actually number and which LED number it is on my implementation. And here you can also tell if you have more LEDs. Some people use additional LEDs for minute indication or second indication, and so you can just increase the number, but here you just enter the number of the LED when for the specific letter. And this function is doing it. It's just checking. It's setting every LED of false so that every LED is inactive. Then it's checking if H and M is in range, the two parameters. And then it's reading the first table and getting the pattern, and then it's reading the pattern and getting every word pointer, and then it's reading every word, and then it's setting actually the LEDs for that. And to set the LEDs, it's actually reading from this table, which is mapping the LED index to the actually letter. Yeah, this is everything for that. So now we can look at the source code and see how everything is working. Okay, we have the main form, and here is actually nothing happen except the save and the load command, and this is actually directly forwarded to the time to words. And the time to words is actually also really easy. We have just a loop over every hour and every minute. And here is the difference. And when you remember in the minute table, we had the difference when when you want to have the hour before or the hour after, then this difference is actually used to shift the pointer like one up and one down, what you actually need. I don't know how in French or in Dutch or in other languages this is handled. So I hope it's flexible enough to do everything what is needed. And if not, you have to fill like for every minute, but in the end it's also possible. Okay, when this is finished, we get a list of every time text, and this list is then forwarded to the words to graph form. First, we can look quick at the structure of time text. It's just a class, and it has actually the hour and minute saved and the corresponding sentence. Nothing more is happening here. we have a toString function and a possibility to check if two time texts are equal, but nothing more. So to understand how we convert the sentences into a graph, we first have to look at our graph structure. I try to use as simple structure as possible, so I have a class which is actually called graph, so it's represent one graph, and this graph has nodes in it, and there is also a start and an end node to have more possibilities for handling, so it's a little bit easier. This code is not very clean because to generate a node for a graph, you have to do it externally, and actually this is bad. There should be functions to add nodes, there should be functions to add edges and so on. But yeah, I didn't do that. It's just, you can see it as a data structure or a data container. So it's actually not clean implementation for that, but it's working for me. Then we have the node structure, and there we have a set for the incoming and the outgoing edges. This helps a little bit in some steps of the algorithm and to understand which edge is which. And then we have also a list which keeps track in which time sentence, so in which text, in which sentences the word of this node is present. This we need later to reconstruct everything back from the graph. There's also a function to test if one edge is reachable to another edge. Side comment again is that this graph is actually directed, so there's just one direction through it. And actually in the whole implementation, I'm just using it as a DAG. So it means there is also no cycle. And this makes sense later when I explain it. So, and then we just have the edge structure and there's nothing. Like it's possible to see where the edge is going when you have the edge itself. It's useful in some situation. Okay, so every algorithm what is actually happening in the whole program happening inside here, I use swing worker. I actually modified it, so it's called my swing worker because I had some problems with the stability of the Java swing worker. First, I get like the list of every time text, and then I'm actually building the graph. And to do that, I get the text of so I get the sentence from every time text. I split this into the words. Therefore, I use a regular expression. And for each word, I generate. I first look if there's actually a pass through the graph. So in the beginning, it's doing already some optimization so that the graph is not exploding. In some cases, it can. So it's trying to make the graph minimal. So not add some edges if they already exist. And if it don't find an edge, a node and an edge, then it's generating the node. So it's making a new node and it's also making an edge and adding that till it's reached the end, and then it's connecting the end with actually the end node of the graph. And that's it. And then we're coming to the algorithm what actually is searching for nodes which have the same text or subtext, and then it's adding them together. For example, you can have a one and one time, or I don't know, it's just an example, and this is actually a subword, so you can match one into time, one time, and then actually these algorithms can find that and can match two sub-expression together. What is actually not happening here is that 1 and 11, there would be a common letter, but this algorithm is not matching it. This is happening in the next step if there's a possibility to use this kind of optimization. Okay, what I want to do is I just want to add nodes which have the most to do with each other. So if you can imagine you have hour and minutes nodes, and you actually don't want that hour and minute nodes get merged. maybe in some really special cases, but not in general, because when you do that, you have to maybe add some other hours again to get some other sentence working. So this will mix it up. If you try to make the letter matrix by hand, you will see what I mean. And this is actually what I want to explain, is it's not allowed to have a cycle in this graph. If this graph has a cycle, that meant that one word is indirectly dependent on another word. And this means I cannot put it into the matrix because I cannot resolve the dependence. So it's not allowed that after merging two nodes that there will be a cycle. To just join nodes which are really neighbors or really are really the same or not making a bad consequences if you join them, I'm just start to search for nodes which are near each other. For that, I make a breadth first search, and I just join nodes which are near in the breadth search sense. And if I don't find any, I try to do it reverse. So first I start from the beginning and work into the end, and then I start from the end and work into the beginning. This is this this loop for, and then I restrict the changes. I also in the beginning I also only allow changes that will introduce a new edge, and so changes which just combine and there's no new node introduced. It's perfect. You can do this without worrying, and then if there's no possibility found, then it will start to allow one new edge, and after that two new edge, and so on. So I try to first map things, merge nodes. They are really have the same neighborhood, don't introduce new edges, and so on. So I try to guarantee that I don't make bad merges, and so I think it's a good way to guarantee that the result graph is as small as possible. But this is just an heuristic, and it's I think this problem is in general NP hard. So if you want to solve everything, you have to consider each possible matching of each node and then check if the result is valid and if it's the smallest. So this would be a completely enumeration, and this will just explode, and it will not be solvable even for these little problems with, I don't know, 300 nodes. So the next step, what is the algorithm actually doing? It's building two lists, and the two lists actually is the list which nodes are compared, and then it's doing actually the comparison. If it's reverse, it's just switching the two lists, and then it tries like if one text is containing the other text, this is good. And then if this is true, it will actually see which edges it have and which edges will be introduced. And if the new introduced edges is less than our level, or our as I told before, our given limit, then it actually will do that. And if not, it will not do that. So if everything was working fine, it's copying every data from the one node to the other, then it's actually adding all edges, and in the end it's removing the matched node. That's it. So there is not so much to it. It's just hard to find the right order to do these limits, and you have to just run a lot of tests, and then you see, okay, this way is actually working good. Okay, and in the next step, we have the finished graph. So we have to match the graph into the matrix. So I'm exploring like every width and every height of the matrix. So I try to get as much different matrices as possible. And for each matrices, I am trying to fit the text. And I was a little bit trying with topological orderings and trying to explore the whole search space. And in the end, it was actually too hard. Like it took too long, or it didn't come up with good results. So I just decided, okay, I will make random heuristics. So I will work with chance, and if you're lucky, you get a good result, and if not. And in the most cases, this works really good because there is not actually a lot of possibilities what you can do. So the random process is actually covering a lot. So what I'm first doing, I'm introducing a new data structure where I can save which words are in which line of the matrix and also save the actual state of the line to see if another word will fit or not. And then I'm going through, and every time I remove a node, there will be another 3 nodes. So I can just add words into the matrix when they are not dependent on any other word. So it means in the sentence it would be the next word. So every word before in the sentence already used. So this word is the next, and so I can fit it. If I mix that up, it will make no sense. Like it will be mixed up minutes and hours. So you cannot read the result because it's not in the right order. So I keep track of 3 nodes, so I have a list of nodes actually already removed. And when I then check through every other node, I can calculate the 3 nodes which are not depending on each other. And then I try to fit every 3 nodes. And when you fit a node, you have to understand, is the word before directly coming next? So if the 2 words are next to each other in one sentence, you have to insert a space. And you also can check if this is not the case. You can also check, do the word overlap each other? And when they're overlapping each other, this will save, for example, one space. So I'm calculating that. And then I'm randomly picking one which is matching. So give me 1 second. This is actually happening here. So I calculated every possible every possible possibility I have, and then I pick one randomly. And that's it. It's doing this. It's continuously doing that till the matrix is full or no nodes are empty. No nodes. So every node is used. And in the second case, when every node is used, we have actually a valid solution. And this is doing it as many as possible. And if we have one fit, we finished for this matrix, and we're searching for the next matrix, for the next smaller or with another dimension. And yeah, that's it. In the last step, we have the graph to matrix. Actually, it's happening in word to graph. Is actually the fitting into the matrix is happening. The only stuff we're doing here is actually choosing the random letters to fill and distributing the spaces over the whole line so that not the words are in the beginning, so it's randomly distributed, so it's not obvious which word are in the matrix. So a little bit randomness can help there. And the actual step what's happening here is the export. And in the export, actually, it's not much work anymore. We have just go through and find every word. There is a little bit tricky because we also allow to have subwords, as I told before, one at one time. When 2 words are mapped, actually make an own entry for the word list. And then I go through, and this is the list of every word. And then I generate all different patterns, and there actually it's not very performant, but it's working. You just make a string representation. So a string with everything is 0 of the length of the number of words which exist, and then it's just set in 1 if it's using the word, and then 0 if not. And then I make a hash set or a hash map in this case, and if I have found every different pattern, then I generate just a list of every pattern. And in the last step, I just go through every hour and every minute and just put out the corresponding pattern to the time text. And that's actually it. There's just not the mapping table is generated automatically, and it's filling this with 0 to the used letters, and then this function is fixed. So there is no modification. So I just wrote the function, tested it on an Arduino, and insert it here. Yeah, this is everything. I can just for fun start the program again, and I hope I find it. Okay, this is maybe not so good. Yeah, this is just a random example, and I will run it and to see a little bit of graph pawn.